It's been a while since I've made a video, so I thought I would show you what I've been working on for the last few months, which has kept me busy enough that I've not been able to make videos. This is a lighting installation that I made for a church, for Christmas carol services. I thought I'd take you through the system because it's quite interesting. So we made these stars, these hanging double-sided LED covered stars. And there were 50 of these put up in a marquee, and each one was individually controlled. So I designed and built them, and also made the control electronics to drive them. And in this video I'm going to show you how the system worked. So let's start with the controllers. I had these circuit boards made on jlcpcb.com for really very cheap indeed, 10 by 10 centimetres, and in 10 by 10 centimetres I managed to fit 16 channels of control. I decided to use network connectors and network cables to link everything together to keep the installation nice and easy, and these boards break out 16 control channels. In the end I didn't need these 4 on any of them, so there were actually 4 control boards in the entire system. Here are the other 2. The number of stars meant that I didn't need these 4 on all these channels, and this was my least reliable channel, because if you look at the back of the board, the way that it works, there's much less copper supplying a power supply to that channel than on the others. These areas had to be much thinner than they are on the other channels because of these tracks coming down here, so I decided I didn't need 4 on each one, so I decided to make it those 4, just for safety really. So the way these work, you've got a Texas Instruments chip on the back, which is a TLC 59401. Now that's a PWM generator, which can generate 16 channels of 12-bit PWM, all independently from each other under SPI-ish control protocol, which is proprietary to that chip. And what I've done, it's designed to drive low power LEDs, and what I've done is used it to power MOSFETs. So each channel on the back has a MOSFET and a polyfuse, and you can see that the polyfuse has been bypassed because I accidentally bought the wrong size polyfuse. And a last minute thing I had to do was to just bypass all those polyfuses to make the installation work. That's what you have to do when you're up against a deadline sometimes. And you can see each one has a resistor on the gate, which is a pull-up resistor in this case, and then the outputs on this are actually open drain, so they pull down. So the resistor pulls the gate up, and the PWM chip pulls the gate down. And then the MOSFET high side switch is the output to each star. The whole system runs at 12 volts. Each of those tiny little SOT23 MOSFETs is 5.2 amps rated, which I found completely unbelievable, but it does work at that current for something that small, and they don't even warm up. Now the way I've done the power supply topologies, the whole system has a common ground, which are these 4 center pins, and you can see that the grounds do actually connect across here. And then each group of 4 outputs has its own power supply connection, so its own terminal block on the top with the pluses on the outside and the negatives in the middle. That's because this whole system uses quite a lot of current at 12 volts. Each star draws 4 amps of current when it's going full whack, which is 48 watts. And I didn't want to buy a single power supply which was 200 amp rated and try and deal with the track sizes on the circuit board, so I decided to split it out into potentially 16 power supplies, although I didn't use quite that many in the end because I didn't need one on these masked off channels, so I only actually needed 6 per pair of control boards for a total of 12. So we went on eBay and I bought an awful lot of these inexpensive closed frame power supplies. Each one of these is a 20 amp 12 volt power supply, and they were astonishingly cheap. I think they were £7 or £8 each, and I've actually modified each of them to produce 15 volts instead of 12. Now you can see on here each pair of boards has got one of these ESP01 Wi-Fi modules. These were used for the control data, and I'll get into that in a bit more detail in a minute as well. Now here you can see the inside of one of these cheap eBay power supplies. I bought these as a job lot of 20, and I'm actually fairly impressed. The quality, well, the manufacturing quality is appalling, but the design is actually quite good. You can see that there is actually a series inductor on the output and some nice capacitors. They're relatively clean. They're certainly clean enough to drive LEDs. You can see that there's a primary switching transistor back here, which is quite well heat sinked to actually a reasonably thick aluminium chassis. And then this is actually the output diode here, and that has got a mega heatsink on it, which is great actually. And these things, even at full load, they don't get that hot. And then you've got plenty of input capacitance there. Capacitance, nice big transformer. And then over here, you've got the feedback resistors that set the output voltage. And here is the opto isolator that actually links the primary side back, the secondary back to the primary side. So what I've done, I reverse engineered this output circuit and figured out that if I put this resistor here piggybacked on top of the main feedback resistor, then I can change the range, the adjustment range of this potentiometer. So out of the box, this potentiometer does plus minus 10% with 12 volts as the centre. With this resistor on top, it does plus minus 10% with 14 volts as the centre, which meant I was able to adjust each power supply from about 13.5 volts up to about 16 volts without any problems at all. You can see that these are actually 25 volt output capacitors, so there's no issue there. I tested these at full whack at 15 volts at 20 amps and sat it going like that for an hour or two just to see what would happen, and it stabilises at a temperature that you can quite happily put your hand on top of. I did actually dismantle and check all of these power supplies. It's generally a good rule of thumb. Anything you buy on eBay that plugs into the mains, take it to bits, check to make sure that it's been wired up properly. And one of the things that I have found on these is there was a lot of sort of solder debris and residue on the circuit boards, which could have caused, certainly would have compromised in some cases, the isolation. You can actually sort of see it through the circuit board. Here is a gap in the copper. This is the isolation distance on the power supply. You've actually got a protective earth running between the two, which is great, although you don't have it here. So this really is actually the sort of danger point in the whole power supply. And that isolation is reasonably good. There's a good sort of 6-7 millimeters of clearance there. There were some bits of solder and debris on these, which I've had to clean off. So yeah, I would definitely recommend anything that plugs into the mains that you buy off eBay. Take it to bits, clean it, check the design, and make sure it's earthed, which in this case these all were. In the installation, these were all earthed. And they were up out of the way as well. They were up in the ceiling, so there was no way anyone was going to be able to touch them. And I stress tested them all at maximum load under close supervision before doing the installation. So I took the view that with those precautions in place, using cheaper power supplies was a safe compromise. Right, now I want to show you how I made the stars themselves. These are all made from a material called Foamex. I bought some Foamex sheets. I bought 3 sheets. Each was a 6 foot by 8 foot sheet. And from each of those sheets I was able to get around about 25 of these stars. I actually made close to 60 in the end. There was some wastage. And they were all hand cut with a scalpel. So the very first one was done with a template, which was made of cardboard, which I reinforced with copper. So here is the positive template. You can see. And that was stuck down with some double-sided tape. Stick it down. And then take a scalpel and trace around the outside of the design. That leaves a mark. Can be freehand followed, and you can actually cut right the way through this stuff with a scalpel. It's a bit tough, but you can get through it. And then once that's cut out, this guy could be laid on top of the completed star, and by lining up the points of the corners where the other points met, that could be stuck down, and then the inside traced like so. And then the result was a second line that I've not drawn very well in this case, but a second line which you could then cut the insides out. And that's how these were all made. And the LEDs themselves were bought on reels. We ended up buying 50 5-metre reels of this tape. This is the 120 LED per metre variety in warm white. These were cut into sections and stuck, and then each section had the end removed by hand, and then they were all hand wired together to complete the circuit. And there it is. So this is white Kynar wire. It's actually for wire wrap, and this is insulated in PTFE, so the insulation doesn't shrink under soldering temperature at all. And you can get very effective stripping tools for these that look like this. And then once that's finished, the whole thing was sealed in hot melt glue. So this would just be a blob of glue on the final design to make it waterproof. Now, along with these circuit boards back here for the control, I also had a set of breakout boards made in white. It was a very small board that fits there, which breaks out the footprint for one of these jacks, a horizontal rather than a vertical version of this jack, on here onto just 2 exposed pieces of copper that I could then wire onto here. So each star ends up hanging like this from its Ethernet cable in the ceiling of the venue. And this is the remote control. So this box is actually a controller I put together for a DMX system. So we had a DMX output on the side, and then a set of 3 faders, a display, and some bank buttons, which, I mean, it was thrown together in literally less than a week, so it's very crude, but it does work. Now, the faders in here are actually motorized, so when I touch them, they're touch sensitive, and if I move them while I'm touching them, you can see the value on the display updates. However, if I try and move one of these with something which isn't conductive, you'll see that it actually fights me and goes back to where it was, because these are motorized. And that motorization means that when you change bank with these buttons, the values here update, and these actually shift to the positions for the new screens. The firmware for this system didn't actually need more than 1 bank, so the firmware it's running at the moment doesn't do that, but it has the capability to do so. So inside, we've got a complete rat's nest. You've got the tails for the bank buttons coming through. You've got the display, and then the 3 motorized faders. The main breakout circuit board that makes all the interconnects here. So these are motor drivers. Each of these is a 2-channel motor driver. They drive the motors for the faders. You've got a 5-volt power supply there. The linear regulator on here hasn't really got enough current capability to drive the display and the RS485 interface, so it was better to just give it a bit of help. And you can see in here we've got a Wi-Fi module, which I haven't screwed down, but I should. And this is the same Wi-Fi module that's on these, with a 3.3 volt linear regulator on the back to power it, and a resistor just to do the logic level conversion for the UART from 3 volts to 5. That works quite well. On here you've got an Arduino Mega, which is kind of controlling it all. A whole mess of wires plugging it all together. These are the breakouts for the display. Just interface it to the Arduino, and this is an RX485 transceiver, which is doing the DMX output. These resistors here are each a mega ohm in value, They're doing the touch sensitivity on the faders. So each pin, each input has a mega ohm resistor going to an output. And what you do is you drive everything low, and then you turn your 4 inputs into inputs again, high impedance inputs, and you drive the one output high, and you measure how long it takes for the input to reach its on threshold with the amount of current going through that 1 mega ohm resistor. So you can think of yourself attached to the pin as a capacitor to ground, being charged through a 1 mega ohm resistor. And the longer it takes to charge, the more capacitance there is. So what you end up with is a time constant that says it takes 5 milliseconds to charge up to whatever the threshold voltage of the logic level input is. And that time constant will change depending on the capacitance attached. So when you touch the fader, the time changes, and the Arduino can detect that. There's actually a library built into Arduino for doing that for touch sense, and that's how that works. This is an off-the-shelf 12-volt switch mode power supply. It takes mains in. This system is not earthed. It really should be, because you can touch metal on the front. And gives 12 volts out, which goes into the board just there. Now this really should be earthed. Oops. Yeah, so that's the control system. And the way it works, this guy broadcasts the Wi-Fi, becomes the access point. And these two look for that access point and join it. And when they find that access point, they make connection and they join that Wi-Fi. As soon as these two join a Wi-Fi, they set up socket servers. They actually open a socket listener waiting for a socket connection, each on a different port. This guy, as soon as it gets a new client attached as an access point, goes and tries and connects to a socket server. So what we end up with is a TCP socket connection from here to here with this as the server, but this is the access point. And that means that I get a data pipe from here to here where it's very tolerant of anything disappearing. Everything has retries built in, so if this disappears, these two obviously aren't connected anymore. They shut down their socket servers and they sit there listening for a new access point. And if an access point with the right name shows up, they'll try and join that Wi-Fi. This guy, if one of these vanishes, will just keep talking to the other one. He's quite happy with that, but it'll sit there and wait for a new connection. So this has actually got a five deep connection buffer. And what it'll do is every new connection that comes in, it will attempt to open a socket server to it. And if it can't, it'll just ignore it. It'll sit there in the table, but it'll say, okay, that isn't actually a proper controller. Someone else has just joined my Wi-Fi. Which shouldn't happen because it is password protected. But the system is tolerant of that scenario. So basically, it's pretty bulletproof. And these guys, you can give them macros and tell them to just do a thing. And that might be random fading, it might be a cycling of brightnesses up and down all in step, or it might be just a constant brightness level for each individual output. And they'll just keep doing it. So if this vanishes, these will just keep doing whatever they were doing when they last had control input as well. So the whole system is kind of designed towards the show must go on. The whole system will keep working. Unless there's a catastrophic failure, essentially. I think at this point I'm going to show you some video of what the installation looked like, and we'll finish the video there.